Hello and welcome to video number 3 of the first week of Meteorology 107. We'll be going into, the fundamental properties of the atmosphere. So when we're talking about the atmosphere, we first consider it's a fluid. You gotta make sure we have waves and we have patterns showing up that you'd consider in any sort of fluid. And it's a fluid in motion. We have wind, we have cyclones and waves and things moving around because the air is moving in the atmosphere. Again, it's a combination of gases. It's a fluid that is a gas. So we have to consider the different combination of these quantities of gases when we talk about the atmosphere, what makes it up. It also has a vertical structure that's important, and we'll get into more detail about this vertical structure going from the lowest layer, troposphere, where all of our weather happens, to stratosphere and mesosphere, thermosphere, exosphere, all these different components. Again, sort of the secret to let you know right away, troposphere is where our weather happens, and that's where we'll be focusing our attention for basically the rest of this class. It also has horizontal organization. We have weather patterns and different distributions of where things happen horizontally over the spatial extent of the planet Earth. And also, in an overall physics sense, the atmosphere is sort of a heat engine. It acts to redistribute heat because you have energy coming in from the sun and solar radiation. It ends up heating up the Earth's surface and to a lesser extent directly the atmosphere, but it does so unevenly because, one, the angle based on Earth's tilt that the solar radiation comes in at makes for differential amount of effective area that's heated up, as well as the response of different land surface types, be it ocean, dry land, vegetation, ice. They all heat up differently. So we get differential heating, we get differential amounts of heat. So that has to be redistributed. Physics and these gases, these fluids, tend to act towards equilibrium. It wants to balance things out. Of course, we never reach that balance in the atmosphere because, again, it's continually fed and there's continual release in an uneven fashion. But the overall action and what weather is this redistribution of heat to tend towards an equilibrium. And if we want to go to the very base level of what the atmosphere is, again, it's a gas. So we want to talk about the fundamental properties of a gas. And this is the one thing I hope you remember from a high school chemistry course, is ideal gas law. PV equals nRT. Again, we'll talk about each of these individual components because they are the terms or the variables that describe the gas that is air, that is what makes up the atmosphere. So P is pressure. Pressure is a force per unit area exerted by the gas. Volume, how much space the gas takes up. Again, if you think about it as geometrically, you have sort of a width and depth and a height. 3 dimensions, you have volume. N is the amount of molecules. In this context, we talk about moles, a particular way of counting the number of molecules. That isn't just the individual number, it's Avogadro's number, very large number of individual molecules. We have R star, that's how we express the universal gas constant. So for any ideal gas, R star is how these variables are related in proportionality, as well as this last one, T, temperature. That's a measure of the average speed of molecules, its representation of its internal energy. However, meteorologists don't like working with the ideal gas law in this form. 2 main reasons for this. 1, we like talking about local properties, so we can describe how everything changes over space. This is sort of in an aggregate sense because we have a particular volume of gas. We don't really want to talk about all of the air in the atmosphere, the entire volume, because it varies. It's unevenly distributed. As well as this amount, it's hard to know the amount of gas in the atmosphere in any precise sense. So we apply some tricks. First thing that we do is, instead of talking about the number, something that's kind of hard to get a handle on directly, we talk about mass, because we have ways of working and considering mass of gas. However, to make that change, now instead of talking about a universal gas constant, we get a specific gas constant. So in order to relate the molecular weight to go from amount of molecules to a mass of all the molecules, we end up coming up with a particular or specific gas constant for any individual gas we have. Or if we take the weighted average of all of our different components of a gas mixture, we can get an R specific gas constant for a mixture of gases like we have in the atmosphere. Last thing, again, because volume isn't a local property, it's over some particular amount, we can divide by volume. And then we get this. We get this nice form, and we have this rho showing up. That's density. That's mass per volume. That's a local quantity. That's a good thing. So we get this nice local expression of the ideal gas law. And this is what meteorologists like talking about. So we have these state variables that describe the state of the air at any given point. We have pressure, density, and temperature. But again, I was saying about that gas constant, it depends on your mixture of gases. It's the weighted average of all the individual components. So it's a constant, of course, if you have a constant gas. But that air in the atmosphere isn't a constant gas mixture. We have some changes. So we have to talk in a little bit more detail about what the gas mixture of air actually is. And so that brings us to this slide. Air itself can sort of be split up, as you see in this table, into two broader components. We have dry air, which is our primary components of air. Again, nitrogen and oxygen are our main contributors. Nitrogen about 78%, oxygen 21%. Argon can't be neglected at 1%, and then you have all of your trace gases here. But this, over the timescales we care about in meteorology, really doesn't change. We can consider this to be fixed. I mean, on the first part, because we really don't see changes over short timescales in our main contributing gases, and even the ones that vary over the course of years and decades, sometimes even seasons, like carbon dioxide, they're small enough that they don't significantly change that weighted average of concentrations that we get to our gas constant. The one thing that does change significantly and cannot be neglected is water vapor. So what we do in meteorology is we split up air into dry air and water vapor, because water vapor is the one thing that changes over timescales that we care about in weather. Things like carbon dioxide, other atmospheric scientists like climate scientists really do care about this because this affects radiation balances. But in weather, we care about the overall combination of these, and we consider it to not change because our dominant influences towards our specific gas constant don't change. Water vapor is the one thing that does. So that's why we have to track water vapor concentration as sort of our fourth state variable to describe a gas. But this is really what we need to describe the state of a gas at a particular point in a meteorological sense. So we have pressure, temperature, density, and water vapor concentration. We often just refer to this as moisture, and not in this video, the next one, we'll talk about the different moisture variables, different ways meteorologists choose to represent this. But in overall sense, these are the four quantities that we need to worry about if we want to describe the state of air. So, going to the first one, pressure. Pressure is, again, physically it's the force per unit area. In the atmosphere, that force is weight. So the atmosphere, pressure is the weight of the column of air above you. We measure it with a barometer. A typical example barometer, like this mercury barometer, again, you directly measure the force per unit area, and that causes a displacement of this mercury column, this fluid, and then we measure this. So again, that's how we get these units of pressure, these inches or millimeters of mercury, this length of displacement in this column. But the typical, more physical unit that we work with a lot in meteorology is hectopascals. Pascals being newtons for force per meter squared area, or millibars, which is just another abbreviation that is equivalent to hectopascals or hundreds of pascals. Again, measured with a barometer. Barometers don't always look like this. In practice, they measure force per area on some sort of metal membrane or something of that sort. But again, it's physically measuring a force per area. If we actually see what pressure physically looks like in the atmosphere, air is, of course, held in Earth's atmosphere by gravity, but it doesn't flatten out. You don't flatten the air completely because, again, air exerts pressure forces. If you try squeezing air, you'll get resistance. So gravity tries forcing it down, but the pressure gradient force, the pressure, will tend to force it. Of course, there's a certain force and a certain compressibility that air has, and if you exceed it, like this packing parcel, you can do that. In the Earth's atmosphere, you don't squeeze out the air because it's all around the spheroid of the Earth. But in general, this pressure gradient force, this resistance from pressure, combined with the downward force of gravity, it balances out on average. And this balance creates this relationship, where we have an exponential decrease of pressure with height. So you have P naught, or P0, your surface pressure. That's the total weight of the column of air above you. And then as you increase in altitude, you end up decreasing exponentially your pressure. So pressure decreases exponentially with height. This is an approximation, but it's a very good one that holds on average very well. So now we get to temperature. Temperature, measure of average internal kinetic energy of gas molecules. You would never be able to measure each of these individual gas molecules moving around, even with an electron microscope. But in the aggregate sense, it's how we describe temperature. And it's measured with a thermometer. Again, you can't measure all those individual velocities, but we can measure temperature and how it affects, say, the volume of mercury or alcohol, and that will cause a displacement in a column like we have in a thermometer in this closed system. So typical units of temperature probably are used to degrees Fahrenheit if you've grown up in the US. Degrees Celsius is more commonly used outside the US or just in meteorological communication. But we also have Kelvin. This is sort of the scientist's unit of temperature because it's an absolute temperature scale. Because 0 Kelvin is absolute zero, where we lose this sort of internal kinetic energy. It limits to zero. And in all of those relationships, those formulas I was talking about before, T has to be in Kelvin or another essentially equivalent absolute temperature scale so that they work out properly. You can't just stick degrees Fahrenheit or degrees Celsius in those formulas. And again, I said measured with a thermometer. Again, it doesn't directly measure the internal kinetic energy. It usually works by way of this volume relationship. Or we have things like thermocouples or thermistors. We won't talk about those. If you're interested, you can take an instrumentation class. Those work on temperature's effects on electricity. If we consider how it varies in the atmosphere in the vertical, this is where we go back to this vertical structure picture of the atmosphere. Now, air heats up or loses heat, is how we describe changes in temperature, through 4 typical processes. Conduction, the ground surface tends to warm up from the sun heating it, and so direct contact, conduction, will tend to warm the air that's closest to the surface. But only the air that's closest to the surface. That's directly interaction. All of the other air ends up heating up mostly through convection, that air moving and circulating and distributing the heat through air movement. We also get changes in air temperature through radiation, both direct visible, just impacting certain gases in the atmosphere, or the main thing, radiating and heating the surface through the sun's incoming radiation, which is most energy dense in the visible spectrum. But we also get the effects of infrared. The Earth's surface, having a temperature, emits infrared radiation. The air, having a temperature, emits infrared radiation. So all of those radiation dynamics end up creating what we see in the atmosphere. The other thing that happens a lot in this lowest level of the atmosphere, the troposphere, where we have weather, this is the layer, again, we care about most for weather, we also get latent heating and latent cooling based on evaporation and condensation of water, because the phase change of water from vapor and liquid, and sometimes liquid and solid if you're going to ice, and those are sublimation, or there's different phase changes. I'll go into those detail later. But those phase changes have heat exchange, and so that will affect the temperature of the air around it. And so all of these processes, in combination with how the air and the quantity of gases in the atmosphere is distributed, ends up creating this squiggly little profile, and we get layers of the atmosphere based on it. In the troposphere, where our weather ends up happening, we get decreasing temperature with altitude. We get our warmest temperatures near the surface until we get to the stratosphere, where because of things like the ozone layer, we actually get direct heating of these gases. And because the pressure is so much lower, again, exponential decrease of pressure with height, there's a lot less air there to heat. So when you get more interactions, it will warm up. The temperature will change, will respond in turn faster. And so we get up to the top of the stratosphere, where you start getting a decrease again, just based on how the gases are distributed. It starts decreasing. And then thermosphere, which also can be considered ionosphere depending on your composition and layering. That is so low in density, your pressures are so low that your ionizing radiation from the sun impacting just sparse molecules will end up increasing your temperature a lot. And so that's how you end up getting this back and forth pattern in the atmosphere that defines the layers of the atmosphere. Again, key points to take away: troposphere is where our weather happens, this lowest level. That's where we get moisture interactions with latent heating and cooling most, and we get a decrease of temperature with altitude. Density, we just calculated. We talked so much about pressure and temperature. Those are the things that we can measure. But because we have this nice ideal gas law, we can just calculate density based on these two. And as an example of that, say we fix pressure at a constant and we increase temperature. So if we increase temperature for our given gas at a given pressure, temperature increasing means that density needs to decrease. So warm air is less dense than cool air. So it has important implications for meteorology, but we don't measure density. We calculate it based on our other quantities. And so that brings us to the end of this part 1. We haven't talked about moisture as our extra state variable. That will be in the next presentation, as well as the motion of the air. We've just been talking about these local properties. We haven't actually talked about air moving around and things changing. So we'll talk about wind in part 2 as well. And again, reminders, discussion posts and quiz for this week are up. And if you're watching this video before Wednesday at noon, there's still a survey up about office hour platform and informal discussion platform. Again, thank you for watching this part 1, and pretty soon, part 2 on moisture and wind as fundamental properties will be coming as well. Thank you.